So, as we were discussing the Markowitz model, Harry Markowitz in 1952 again for the benefit of the students came up with the very simple model where he wants to optimize some objective function based on some constraints. Now, if you remember when we were discussing the utility theory, we did mention that if the returns are normal, then the utility function can be considered quadratic. And what that quadratic function is very heavily utilized in all investment purposes. So, with that assumption that utilities of human beings are basically quadratic in nature, we can safely assume, even though that is not true in practical sense, that the returns are normal, and if returns are normal, then the best parameters based on which you can find out the characteristics of the human being and try to optimize would be point number 1 would be the mean value of the portfolio, which is a combination of the mean values of the stocks, and point 2 is basically the variance of the portfolio, which is a combination of all the variances, the covariances of all the stocks. By the word stocks, I mean all the n number of assets or stocks which are there in the basket which you have. So, assume the portfolio again for the benefit of the students, it has n number of assets, each with the expected return of r. Again, capital R and small r I am using interchangeably. Covariance of sigma I j, I and j running from 1 to n, and suppose that the weights wi's are given for each and every assets. So, weights for the time being we will consider they are between 0 and 1, which means they are no short selling. So, we will switch over from short selling being there, not short selling not being there, such that the optimization problem in its overall context, if you see, would not look much different, but when you solve the problem there would be some not difficulty, the methodology of how you solve the problem would be difficulty. Now, let us bring for the first time that any investor, if he or she is non-satiated, that means more you want, is due to some reason wants the overall return on the portfolio to be minimum or greater than equal to some R star value, which is known to us or known to the investor or known to the broker. Another point would be basically the level of risk for that portfolio, which is also known to the investor. So, you can basically take two approaches: have the portfolio in such a way that the portfolio return would be greater than equal to that R star value, or have the overall portfolio and the weights in such a value that the risk of the portfolio would be less than equal to the so called sigma star value which we have for himself. Again, you may ask, how about combining both of them? Yes, it is possible, where you can basically try to combine both the risk and return in such a way that that combination would result in either the objective function or in the such that constraints that these 2 points of importance, which is returns being greater than equal to R star and risk being less than equal to sigma squared star, whatever it is values wise, would be considered in the problem accordingly. So, our first problem for the Markowitz model very simply would be minimize the variance. This half value has no significance. It is basically, if you see the principal diagonal and of the diagonal element, they are being multiplied by 2. So, this is basically being divided by half which is just a constant, it does not have any much consequence. Subject to this constraint. Now, the constraint I have written as equal to, it can be greater than equal to also, that will not matter much in the conceptual framework, but obviously the solutions would be difficult. So, it can be greater than also. The next constraint is very simply is the sum of the weights is definitely 1, because the weights have to go 1. And the third constraint is the weights of the stocks are limited between 0 and 1, which means there is no short selling. So, in case if we had short selling, obviously this equation would change, the others would remain the same according to how we have formulated the portfolio, given the overall basic philosophy is this: minimize the risk subject to some constraint where the returns of the portfolio is greater than R star value, where R star is again known, and the sum of the weights is 1, but the last one basically being where the weights can be negative also. So, in the previous optimization problem, as we have said, we have not considered this short selling, hence the weights have to be greater than 0. In case if there is short selling, weights can be less than 0 also. Now, if we consider short selling is present, then optimization problem becomes this. Again same thing, minimize the risk subject to these constraints where they are greater than equal to or equal to, the sums are 1, and the wi's are unbounded or unconstrained. The problem could have also been solved in other way, like initially the first two problems were where we were trying to minimize the risk. How about trying to basically maximize the return? So, now your problem is maximize the return subject to constraints where the risk of the portfolio is equal to some sigma star, which I was talking about, or less than equal to sigma star. Weights again is equal to 1, which is true. Weights is greater than 0 for the case when there is no short selling involved. If short selling is involved, exactly the same thing. Maximize the return subject to constraint where the risk of the portfolio is less than equal to some sigma square star, which is a known value. Weights is 1 and wi's are unbounded. Now, for the case when considering SS is allowed, which is short selling is allowed, we use a simple concept of Lagrangian multiplication. Lagrangian multiplication is very simple, where we have basically some Lagrangian multipliers being multiplied to the objective function to all the constraints, and then we basically find the combination of the objective function and the constraints and try to differentiate that combination of the function with respect to the Lagrangian at each and every step. Now, if there are 3 Lagrangian lambda 1, lambda 2, lambda 3, then it will be partially differentiated with respect to lambda 1 put to 0, partially differentiated with respect to lambda 2 put to 0, partially differentiated with respect to lambda 3 and put to 0, and then we find out the solution. So, now if you consider short selling is allowed, after the Lagrangian is formed, the Lagrangian equations are like this. The first one has 2 Lagrangian, which is lambda and mu, and the second one is would bring us back to the original such that constraint, which would be basically going one circle. So, obviously, they would not be utilized. What will be utilized later actually for the Lagrangian is the first one, which is given with 2 Lagrangian multipliers lambda and mu. Now, once we differentiate that and basically find out the lambdas and mu values, we will get 2 extremes. One case when lambda is 0, mu 1 and mu 0 lambda 1, that will give us all the values which are needed in order to basically draw the portfolio which is required for us. Suppose we have 3 uncorrelated assets with variances 1 and mean values of 1, 2, 3. So, if we solve the problem using the Lagrangian, the weights comes out to be as given W1, W2 and W3. Now, notice one thing, if you add up all of them, the value is 1. Now, if say for example, R star value is such that R star divided by 2 is less than equal to minus 2/3 for the third equation, then obviously it will mean that the weights is negative, which means in a way that the actual original condition which you have considered, which is there is short selling, is being again corroborated in the fact that depending on the R star value, we can get some values of weights, which in this case, as I pointed out, is W3 would be negative, W2 is obviously 1/3, which is positive, and the value of R star by 2, if it is basically less than 2/3, obviously this value would not be negative in the sense, and it can be changed accordingly. So, one of the W1s or W3s can be made negative and positive depending on how the problem has been solved. Now, if you see, your question would be, how do we draw the portfolio? Now, look at it very carefully. In our initial problem, we considered that such the constraints are that either the subject to conditions has the returns greater than equal to R star or the risk being less than equal to sigma star. So, these are the values which we have. Now, what we do is simply like this, keep changing R star. So, what if you have this overall Cartesian coordinate where you are trying to draw, as you keep changing R star, you will get different values of W1, W2, W3 as a combination. So, given this values of combination of W1, W2, W3, what you do is that find out the returns for the portfolio corresponding to that value of W1, W2, W3, point 1, and point 2 is that find out the correlation coefficient between the stocks, and based on that particular correlation coefficients, you find out the variance of the portfolio. So, what you are doing is that as you keep changing R star values, you will get different combinations of the weight such that they will lead to 2 different points which are with each other, as in the Cartesian coordinate, one point x, one point y. X would be along the x axis where you are trying to find out the risk, and y would be basically those value corresponding to the return. So, as you find out, you will basically have different combinations of r and sigma. So, change r star, you will have different values of sigma. So, once you are able to draw that, you can get a curve such that overall risk return profile would be exactly equal to the risk return profile which we have tried to explain in a very simple qualitative sense. Moreover, now we want to find out the minimum risk, mean and the standard deviations. So, if you find out the returns for the n stocks, it will basically be r star and the sigma would be given by these values. So, keep changing r star, you will get different values of RP for the portfolio as well as for the sigma. So, once we have that, if you are able to draw, again I am coming back to the case where you are able to draw the efficient frontier with the minimum variance point and the maximum point which is there, and any extension obviously will do, because there is no short selling, you will get the dotted lines, which is the case where short selling is allowed. So, suppose we have two portfolios. After solving the optimization problem corresponding to two different sets of returns, one is R1 star and another is R2 star. So, I am not using the word bar, bar is basically the average. So, R1 bar star and R2 bar star, which is the average values. Now, combining them in some proportion such that the respective weights add up to 1, we can have an infinite number of such combinations between these R1 star bar and R2 star bar, which would give all the infinite points such that we are able to find out the variance, and if the variances are found out, considering the fact that we had already assumed some R star values between R1 star and R2 star, we can definitely get all sets of feasible region, which is basically the efficient frontier. Remember, they are not, I am using the word feasible region, that means that you are taking the best combinations such that you find out the efficient set of points in the efficient frontier, which means that if you have R1 star here and R2 star here, what you are doing is that you are basically denoting different points, and these different points will give you the set of the efficient frontier, which is part and parcel of the efficient frontier, which we have already discussed. Now, this leads us to the fact of two front theorem. So, for example, two efficient fronts or portfolios can be established as that any efficient portfolio can be duplicated in terms of the mean and the variance as a combination of these two. In other words, all investors seeking to basically have a chunk of the portfolio such that they are always efficient, they would basically take this R1 star bar and R2 star bar in some proportions depending on the risk return appetite, such they are able to formulate the portfolio which basically meets their criteria to the maximum possible extent. So, this is the point which I have drawn. A is basically R bar star 1, B is R bar star B, which we are basically denoted as R bar A and R bar B. Given these weights which you have found out, you can find out the sigma A and sigma B and basically plot all the points in between them. Now, the optimization problem under consideration that no SS is allowed was as follows, which we already discussed that. So, there is no nonlinear optimization problem and cannot be solved as shown before, as we have done for the SS case, for the short selling case, but we will see that how we can solve it in an indirect method policy later on. Obviously, there are different type of techniques to solve it, but we will simply solve them in a different methodology, either within another in the next to next set of classes, or say for example by the next class, which will be continuing with the case of optimization in the area of portfolio management. So, we are giving the following data, where the first column are the securities, second columns are the variance covariance matrix. So, if you see the variance covariance matrix, the principal diagonal which you have here, the value 2.330 is the variance of the first one, similarly for the second, third, fourth and the fifth one. So, these are the variance values, and the off diagonal element, this one is the covariance between first and second or second to first. If you see these values, which is 0.56, is basically the covariances existing between the fourth and the second, or the second and the fourth, and the last column which you have is basically the return. So, these are all in percentage sense, but I have just taken their actual values as it is, and in order to basically illustrate what we have been discussing for trying to draw the efficient frontier. Now, for solving the two sets of solution, which if you remember initially the Lagrangian we had taken, and I had mentioned the Lagrangian for lambda and mu, it can be proved that when lambda is 0 and mu is 1 would always give you the minimum variance point, and when lambda is 1 and mu is 0, it will give you the other extreme point, which is the for the maximum case. So, what we mean is basically this is the minimum variance point, which is here, and this point which for which we have the maximum value would be given by the case when lambda is 1 and mu is 0. For lambda 0 and mu 1, if you solve this equation, you get the set of weights which is given. Now, let us pause. We have been always mentioning that the weights should add up to 1. Let us add them. Do they add up to 1? Answer is no. What we need to do? We need to normalize them. A simple concept of normalization would be try to divide that particular value of V, which is basically akin to weights, divided by the sum of them. So, once we do that, we have the weights as given. For the first stock is about 8.8%, second one is about 25.1%, and so on and so forth till the last case, which is 27.5%. Now, your question, do the weights add up to 1? Answer is yes. Check it for yourself. And once we have found out this minimum variance point, what we need to do? Weights are as such are not sufficient. We need to go back to the calculation, find out the weights, multiply by the corresponding returns, and find out the return of the portfolio. So, once we find out the return of the portfolio, it comes out to be 14.13, and the standard deviation or the square root of the variance come out to be 0.719. That is, what you have done is, for the first step, we have found out the minimum variance point between these 5 stocks which are there, where the weights are now given by this combination of vector. That means, if you invest in these proportions, the overall returns and risk are given by 14.413 and 0.791. Second, we need to find out another point, which is basically why we are doing it, because if you remember in few slides back we discussed about the two fund theorem. That means, given two financial portfolios which are there, a person can combine both of them in some proportions to meet his or her risk appetite or return appetite. So, considering that, if we consider lambda 1 and mu 0, we can solve it and find out the next vector, which is V. V is suffix 2. 2 is not a square, it is basically a suffix. If you add them up, what do you see? The weights do not add up to 1. And also a very interesting thing that you find the weights are 300 also, or 365% also in the first case. So, again if you do the normalization, find out the weights, which is given by W suffix 2. So, this vector is when multiplied by the corresponding weights, the returns of the assets, obviously we will get the other extreme point, such that the other extreme point would basically have the return as 15.20 and risk as this, where this return and risk has been formulated by combining this set of vectors which are there for us. Thank you.